So the, the title of today is Understanding and Mitigating Climate Change. And begin with introduction and context. I'm going to be showing you lots of slides, lots of technical material. Please unmute and stop me if you can't understand what I'm showing you. I'm going too fast. Otherwise, please stay muted. And what I'm showing you here right now is a graph of global mean surface temperature of the Earth over the past 22,000 years. So global mean implies average over the entire face of the Earth. Surface temperature over the ocean is the sea surface temperature. Over the land, it's the temperature a few meters above the surface. And there are a couple of things that are visible on this graph. We see the last ice age. This is the recovery from the last ice age. This is called the Holocene warm period that we're living in right now. The approximate beginning of human civilization about 9,000 years ago. This little bump here is called the medieval warm period from 900 to 1200 AD. This is called the Little Ice Age from 1500 to 1700 AD. And finally, we see this red spike here, which in fact is the post-industrial global warming we are concerned with. There are a couple things that are immediately obvious when you look at this record in this time frame. You see that this post-industrial global warming, first of all, it's going in the wrong direction. It's warming. The Earth should be cooling. In fact, the Earth has been cooling for about the past 7,000 years. And the reason it's been cooling, this long-term trend here, is because the Earth's axis has been losing tilt. The Earth's axis is inclined, as you know, but it varies between about 24.5 degrees of inclination and 22.5 degrees, and it rocks back and forth on a 41,000 year time period. That's called the obliquity cycle. It's driven by the gravitational pull of the sun and the moon on the Earth, the fact that the Earth is top heavy. And we're about halfway through that cycle. The Earth's been losing tilt. When the Earth loses tilt, that produces a slow cooling trend and heading towards the next ice age, basically in about 12,000 years. But in fact, we're suddenly warming, and we're warming very fast. In fact, we're warming about 20 times faster than natural climate change. This is what natural climate change looks like. Very, very slow trends. Suddenly, we're going in the wrong direction, warming about 20 times faster than normal climate change. Oh, by the way, this warming began right when we started burning coal as part of the Industrial Revolution. So 20 times too fast in the wrong direction is what's happening here. Now I'm going to zoom in on that red spike, and now we're looking at the same quantity, global mean surface temperature of the Earth, but now we're looking at it from 1850 to 2017, and it's being plotted by year. The previous graph, the time resolution along that horizontal axis was about 50 years. Now the time resolution is 1 year. So you see a lot more detail. What we're looking at is this GMST quantity from 5 different, very credible, independent sources. Some of them use satellite data, computer models, very sophisticated analyses. Some use much simpler analyses, but they all paint the same picture. And that picture is as follows. From 1850 to 1880, not much change, a slight decline from 1880 to 1910, pretty strong upward trend from 1910 to 1945, from 45 to 75, slight downward trend. And then beginning in the mid 70s, a strong upward trend in global mean surface temperature of the Earth, such that we're now running about 1.2 degrees centigrade above the pre-industrial level. A couple things to note here. Look at the very close agreement between these 5 different sources here in the modern era. That's because the climate system is very well observed. We have all these satellites up there and lots of observations. And so we are able to make very good observations there. But also noted that the temperature doesn't go up in a straight line. It's kind of like the stock market. There's volatility here. Stock market doesn't go up in a straight line. Temperature of the Earth doesn't go up in a straight line. There's all these zigs and zags here. These zigs and zags here are not climate change. That's called climate variability. It's things like El Nino and La Nina that we're very familiar with here in California. For example, when you have an El Nino event, you get an upward spike. When you have a La Nina event, you get a downward spike. That's because heat is being exchanged between the atmosphere and the ocean, and that causes these spikes here. But that's not important. What's really important is the long-term trend. And in fact, one rule of thumb I'd like you to take away is that if you're looking at climate change, you really need to be looking at trends that are 30 years or longer. If you're looking at a trend that's 20 years or less, you're not looking at climate change, you're looking at climate variability. 20 to 30 years, that's kind of gray area. You really want to be looking at 30 years or longer. 50 years longer would be even better to be tracking climate change. And I'm going to show you an animation of one of those those products. It's actually the NASA product. And what we're going to be looking at here is an animation of surface temperature anomaly from 1880 to 2018. Now, temperature anomaly is just a fancy way of saying temperature difference from a standard field. And the standard field in this case is the 1951 to 1980 30-year average of the temperature all around the Earth here. And so here's the temperature scale. Where it's white, it's the same as that 30-year average. Where it's yellow or orange, then it's warmer than that 30-year average. So for example, the dark oranges here are 2 degrees centigrade warmer than that average. And conversely, the blues are cooler. Dark blues, it would be 2 degrees cooler than that 1951 to 1980 average. Now I'm going to roll the animation here. I'm going to call out the decades, and you keep focused on what's happening there and pay particular attention to what happens in the 1970s. So here we go. We're in the 1880s, 1890s, 1900s, 1910s, 1920s, 1930s, 1940s, 1950s, 1960s, 1970s, 1980s, 1990s, 2000s, 2010, and finally we end up at 2018. What you can see is the Earth has been warming very dramatically. And a couple of things here. First of all, the land is warming more than the sea. In fact, about twice as fast as the sea, even though about 95% of the heat is actually going into the sea. That's because the oceans have very high heat capacity, about 200 times the heat capacity of the land. So they can absorb a lot of heat without warming up very much. That's good news because it really mitigates the warming that we experience over land and that we're living where we're living. But when future generations conclude they have to cool down the Earth, that's bad news because all that heat is going to be giving up from the ocean. It's going to make it very difficult for future generations, those living the next couple of centuries, to cool the Earth back down, and they're going to have to do that. We also see here that there's more warming the farther you go north. The Arctic is warming about 2 to 3 times faster than the rest of the Earth. That's called Arctic amplification. Also, there's a lot of variation around, for example, North America. You can see all the warming that's been occurring in the Western United States. Of course, with that warming has come drying and hence all our problems with wildfires. There hasn't been that much warming, for example, in the Southeastern United States. And also, it's not warming everywhere. Notice there are areas of blue here, usually associated with changes in ocean circulation where it's been cooling. And when you're talking about global warming, you really need to look at the global average. So what's going on here? Well, in fact, it is the greenhouse effect, as I'm sure you're aware, but I want to take you a little bit deeper into the science on that. And the best way to interpret the greenhouse effect is in the context of the Earth's energy budget, which is depicted here. So the yellow here is the fate of incoming solar radiation from the sun. And the brown here is outgoing long-wave radiation or infrared radiation, which is irradiated from the Earth and from clouds. You might be wondering about what about other sources of heat? For example, what about heat coming up from the Earth's interior? There is heat coming from the Earth's interior. That's how geothermal energy works, but it's very, very small. All other sources of heat are trivially small compared to what's depicted on this chart. It's really the Earth's radiation balance that determines whether the Earth is going to warm up or cool down. So the greenhouse effect works like this. The Earth is warmed by incoming solar radiation, and it's cooled by reflected solar radiation, reflected from the surface, reflected from clouds. And it's also cooled by outgoing long-wave radiation from the surface, from the tops of clouds. Greenhouse gases in the atmosphere trap the outgoing long-wave radiation and warm the lower atmosphere. That's important, just the lower atmosphere, about surface up to about 20,000 feet, and the surface of the Earth. And human activities increase the greenhouse gases in the atmosphere and increase the warming. Now, in order of how much heat they trap, it's water vapor, carbon dioxide, methane, the fluorinated gases, for example, man-made gases used in refrigerants, and finally, nitrous oxide. Notice that I've colored water vapor differently. Although water vapor traps more infrared radiation than any other greenhouse gas, it is not driving global warming. That's because water vapor, water in the atmosphere, is in balance with the natural hydrologic cycle. It also has a very short residency time. If you put a large amount of water into the atmosphere, within a couple of weeks, it's going to just rain out. That's not true of these other gases. These are not these 4 gases here are not in balance with any natural cycle, and they have very long residency times ranging from decades to even thousands of years. So it's in fact these gases that are driving global warming: carbon dioxide, methane, the fluorinated gases, and nitrous oxide. Carbon dioxide is the dominant greenhouse gas right now. It's not the most powerful gas in terms of how much it's molecule by molecule, but there's so much CO2 in the atmosphere that is in fact producing more global warming than all of the other greenhouse gases combined. It's not to say they aren't important. The other greenhouse gases are very important. We have to worry about them, but CO2 in fact is the big culprit right now. So what are the implications of this global warming and climate change? Well, I like to divide them into two categories: natural consequences and human consequences. Natural consequences are the consequences on the human world, or on the natural world. And I'm just going to hit the high points here. Increasing frequency and intensity of severe storms, increasing frequency of life-threatening heat waves. By the way, heat waves kill more people than any other weather phenomenon, both in the US and around the world. Increasing frequency and intensity of floods in wet regions, increasing frequency of droughts and wildfires in dry regions, like the region we live in. Decreasing mountain snowpacks and earlier snow melt, big issue here in California since we derive a lot of our water supply from the Sierra snowpack. Rising sea levels, increasing mortality of coral reefs, known as coral bleaching, decreasing productivity of fisheries, loss of biodiversity. Now, those natural consequences immediately translate into human consequences. And again, I'll just hit the high points: increasing economic costs, increasing competition among nations for water and food, increasing displacements of people leading to unrest, increasing threats to human health, increasing mortality from heat waves, other severe weather events, starvation, disease, and war. Not a pretty picture. So here's where we are right now. In the context of this 22,000 year view, you can see this radical upward movement in the global Earth's temperature, running about 1.2 degrees centigrade above the pre-industrial level. So where are we going? Well, if the world adopts all of the recommendations of the Paris Climate Accord and achieves a net zero greenhouse gas emissions by 2050 and near zero greenhouse gas emissions by the end of the century, 2100, then by the end of the century, we could hold global warming to about 1.5 degrees C above pre-industrial. And that's the goal of the Paris Climate Accord. If, on the other hand, we completely ignore Paris and conduct what's usually referred to as business as usual, in other words, throw up our hands and don't do anything to constrain greenhouse gas emissions, then we'll end up here, about 4.5 degrees C above pre-industrial. You can see how radical this is. You know, this is about the amount of change there is between an ice age and a warm period. You know, it's a huge change happening very abruptly. Well, we're not going there, fortunately, but we're not anywhere near achieving the 1.5 degree goal. Right now, we are on track for about 3 degrees C warming above pre-industrial. Now, ultimately, we'll do better than that. My prediction is we'll come in somewhere about here, about 2.5 degrees above pre-industrial, which is quite a bit worse than the goal of the Paris Accord, but quite frankly, I think that's where we're going to end up. And you can see even there is quite radical compared to you know, what's experienced during human civilization. If you think back here, here's the beginning of human civilization, 9,000 years ago. There's been very little change. It's a slow cooling trend, and then suddenly these very rapid upward spikes. So that's a big issue. So what needs to be done? Well, I'm a big fan of Project Drawdown, and you can visit their website, drawdown.org. They also have a best-selling book out called The Drawdown Review. It was founded in 2014 by Paul Hawken, and Project Drawdown presents 82 solutions for reducing greenhouse gases by avoiding emissions and or sequestering carbon dioxide already in the atmosphere. These solutions consist of technologies, practices, and policies organized into 9 sectors and implemented in 2 scenarios. One scenario was achieve hold it warming to 1.5 degrees centigrade. The other is hold it to 2 degrees centigrade by the end of the century. Essentially, Drawdown provides a roadmap for stopping and eventually reversing global warming and climate change, a roadmap for the governments of the world, essentially. And so here are the 9 Project Drawdown sectors, and they're kind of organized like this. Electricity, food and agriculture, industry, transportation, buildings, these are all geared towards reducing emissions of greenhouse gases. So for example, wind and solar energy generation would come in here. These are land sinks and coastal ocean sinks. These are geared towards protecting and enhancing the ability of the natural world to remove greenhouse gases from the atmosphere, taking care of our forests, taking care of our coastal wetlands, that sort of thing. Engineered sinks, this is about developing artificial means to remove greenhouse gases from the atmosphere. And finally, health and education, which is about limiting global population growth, which is in fact an important part of the solution here. I'm also a big fan of this book by Bill Gates, How to Avoid a Climate Disaster. There's a lot of overlap between Bill Gates's book and Project Drawdown. They talk about some of the same technologies and ideas, but Gates approaches it from the standpoint of a businessman, from an entrepreneur. And he's also very tech savvy, of course. And he talks a lot about what it takes from a business standpoint to get where we need to be, talking about reducing the green premium, for example, things like that. So I do highly recommend his book. So closing comments, and then we'll open it up to question and answer. There is an overwhelming international scientific consensus on the following 3 points. Number one, over the past 120 years, the Earth has been warming and the climate has been changing at alarming rates. Number two, global warming and the resulting global climate change over the past 120 years have been driven almost exclusively by the Earth's greenhouse effect and the accumulation of greenhouse gases in the atmosphere caused by human activities. And finally, number three, without dramatic reduction in the emission of greenhouse gases into the atmosphere, the Earth will continue to warm and the climate will continue to change to the detriment of humankind. Stated succinctly, climate change is happening, it's being driven by humans, and it's not a good thing. Now, there isn't a legitimate science organization in the world, by the way, that would disagree with those 3 points. And in fact, this is a partial list of leading science organizations that have issued formal statements confirming human-induced global warming, and it's a very impressive list, as you can see here. So finally, actions you can take as an individual. Well, first, learn the basics of the science behind why our planet is warming and the climate is changing. And by suffering through my talk today, you've taken a big step in that direction. Use your position of leadership in the community, and I know you're all leaders, to advocate for climate action. Whenever you have an opportunity to interact with other leaders in your community, be they political or otherwise, let them know that you want to see action taken on this issue. You can join an advocacy group, such as the Citizens Climate Lobby, and participate actively. And finally, vote for candidates who will address your concerns about climate change. So that's it. I'm going to stop the share now and open it up to question and answer. Got a question? Just go ahead and unmute. And
Mike, when you were showing us the picture of the world and explained the kind of temperature chart, so to speak, and then you ran through the decades.
The animation, yes, the animation.
The animation. Mm-hmm. What I was confused by was the intensity in West Africa through several of those animations. Yeah. And then in the end, West Africa appeared sort of relatively neutral to the others. Mm-hmm. And I can understand, you know, we're burning the rainforest for places to grow cattle for meat.
Right.
And I could imagine that being a hot zone, so to speak. What was it that was happening in West Africa?
There's just a lot of variability that occurs around the world. And, you know, it's hard to pin that down to exactly what's specifically is causing that. But there's a lot of variability. You really kind of need to look at the large trends. You know, the land is warming more than the sea. The Arctic is warming more than the low latitudes and that kind of thing. But individual variability, it's hard to really pin that down in terms of individual countries and so forth.
Thank you.
Mm-hmm. Your temperature,
yes.
Well, your temperature shows sort of like a bell curve over the millennia, and we were just starting to go down that curve, and then
right.
You know, I know it's not going to be a solution, but is there any way that the as it becomes steeper going down, that would help to mitigate if we were going into an ice age.
Right.
It'd be, countervailing, kind of tugging in the opposite direction.
That's true. That's absolutely true. Let me talk a little bit about the ice age cycle. For the past million years, we've been on a 100,000-year ice age cycle. So we've been through about 10 ice ages. By the way, the ice age is the popular term. Technically, it's called glacial period, interglacial period, but the popular term is ice age. So the way that works is we're in an ice age for about 60,000 years. Then it takes about 10,000 years to come out of the ice age. Then we're in the warm period between ice ages for about 20,000 years, and then another 10,000 years to go back into the next ice age, and the cycle repeats. So 100,000-year ice age cycle. Right now, we're 12,000 years into the Holocene warm period. So that means we've got about another 8,000 years to go before it starts to turn down. So what you say is absolutely true, but you'd have to wait about 8,000 years for that to happen. Right. More questions?
I was interested in, you talked about in that graph, you talked about the 9 different areas, and there were 3 that were sinks.
Yes.
Can you explain that a little bit, especially the engineered sink?
Yeah. Well, we're putting CO2 into the atmosphere about 2 to 3 times faster than natural world can take it out. And about 35% of that is being taken up by the land, and it's being sequestered into the soil by the roots of plants and trees. And that's what we really want. That's really, really good. Mm-hmm. About 20% of it is going into the sea. And that's not so good because that's contributing to reducing oxygen levels in the sea, which is hurting fisheries. And also it's causing ocean acidification, you've probably heard about. And so that's not so good, but at least it keeps it out of the atmosphere. And the remaining 45% is accumulating in the atmosphere. So the idea is we want to first of all, reduce emissions of greenhouse gases, but also enhance the ability to take greenhouse gases out of the atmosphere. So that's trying to stop deforestation, particularly, for example, in the rainforests like the Amazon, taking care of grasslands, worrying about peat bogs and coastal wetlands, which are very good sequesterers of CO2. Unfortunately, there's a lot of deforestation occurring around the world, and that's going in the wrong direction. We need to reverse that trend. The engineered sinks are the artificial means. It's usually referred to as direct air capture, and there are technologies that have been developed to actually extract CO2 from the atmosphere and use it, sequester it away. That does work, but it's very expensive. If you looked at what it takes to scale that up to really to make a difference, it's beyond what would be viable. Now, I'm not saying research shouldn't go on in that area. I'm glad people are working on those kinds of things. But quite frankly, I don't think that's going to become a major part of the solution. Probably become part of the solution, but not a major part of the solution. One thing we have to worry about is there's not going to be a silver bullet out there coming along, some technology that somebody's going to invent, that's going to suddenly solve this problem for us. I just don't see that happening. We really do need to double down on reducing our greenhouse gas emissions, and we need to take care of the natural world.